Hello again everyone, welcome back to ptet.chemistry channel. So my name is Dr. Ont, and in this tutorial video I'll go through this restructured format kind of A-level chemistry tutorial for the Cambridge International 9701. This is for the June 2021. It's a recent summer 21 exams. This is a paper 4 variant 2, so it's one of those really long tutorial as a result of it being my line is not straight, I beg your pardon. Yeah, it's one of these really long tutorials in paper 4 where I actually think out loud and I try to go through concepts that are not just directly what the question asks, but also the associated or the related concepts that I think are relevant and important recap for you or for anyone else who are watching this tutorial video, I guess. So if you think it's too trivial for you, just feel free to skip on to the next question. But if you feel they are useful, then at least by not going through all the tutorial videos, but by going through just selected ones, you will still be picking out useful things along the way. So that's the whole purpose of my tutorial videos, where I focus more on the learning and rather than just doing the exam paper itself. And for that you have the marking schemes and you have many other resources to refer to. Okay, so before I do get started, so make sure you support the channel by clicking the button on this bottom right. To subscribe to the channel is entirely free, and to get notifications and updates, do turn on the bell button, and follow me at ptet.chemistry on Facebook, Instagram and Twitter to get connected, to send in questions, messages of your achievement, your struggles. Look forward to hearing from you. Okay. So let's get started. In this question 1, so this is a transition metal chemistry. So they first wanted us to do this electronic configuration of this gaseous ion. So it's more like a AS level question. Before you do that of a transition metal ion, you should try from the atom first. So I'll do chromium atom. Chromium atom from the periodic table, I start off from this simplified argon notation. So there is up to argon, and then I fill out the 4th row of the periodic table. So there's potassium and calcium, so it's 4s2. You count the element in the D block: scandium, titanium, vanadium, chromium. So it looks like 3d4, and this is actually wrong from your AS chemistry because they repel more. When you put the 2 electrons in the S subshell, it's much better if you promote one to the D subshell. At least then they are occupying each of the D orbitals individually and pointing in their own directions, such that they repel lesser. The electron repel lesser, so this is favored, this is slightly more favored, and this is the adopted configuration for chromium atom. The other case where this also appear is in the copper gaseous atom. Copper atom without any electrons having been lost, it's copper being argon 4s1 3d10. Okay, now we fill 4s before 3d, but we also lose from 4s before 3d for the transition metals. So what happened then is I lose one there, I lose my second one there, and then I lose my third one there. So if they ask for chromium 3 plus, which is what the question is asking, chromium 3 plus, I'll have argon, I'll have 3d3 because I lose the first one, and then I lose 2 more from there, so 5 minus 2 is 3. But of course they want us to complete the electronic configuration in the complete manner. So 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d3. That would be the correct configuration for Cr3 plus ion there. A part 2, they want us to define what is meant by complex ion. So it's an ion, so it's an ion formed by ligands connecting or bonding to, forming by ligands, forming dative covalent bond, or you might call it coordinate bond, whichever one you like, just stick with one form or the other. So forming dative covalent bonds or coordinate bond, as I mentioned, to the metal ion center, So essentially when you have a complex, you have ligands, you have a metal center, and these ligands form covalent, dative covalent bond to this metal ion center. Then we call them as complex. Part B, so question 1, part B is about, they say it shows similar reactions or similar chemical properties as cobalt chemistry. So chemistry of cobalt 2 is actually in your syllabus together with chemistry of copper 2 plus. So you should really know them very well. So we have NaOH, which is just acting as a base, OH minus. We have H2O2, which can act as oxidizing agent, and we have NH3, which can act as both initially as a base, and then in excess is going to be a ligand. So in terms of the reagent added, and then we have to describe the formula. Well, we have to get the formula of the chromium species form, and we have to identify the type of reactions. So we are not being asked for any equations or whatnot here. We're just being asked on, well, what happened in each case. First of all, you have NaOH aqueous. So this is the source of hydroxide. Hydroxide precipitate out the cobalt as cobalt 2 hydroxide, and that is like, it started from this solution, which is kind of like a pink solution. So they haven't asked us to describe the color of these things with the chromium species, because the chemistry of chromium compounds are not specified in your syllabus. But of course, we know that the cobalt species were in the presence of NaOH. I think I better move this table to a new page, because I want to talk a lot more about this than the space given. So what happened then is the cobalt species, if I do NaOH aqueous, I'll get a cobalt 2 hydroxide, and this is a blue precipitate. And if I have H2O2, we know that we get this disgusting brown solution where the cobalt actually get oxidized to cobalt H2O6, but now it's 3 plus, because it's the oxidation of the cobalt 2 to cobalt 3. Actually, I beg your pardon, it's not a brown solution. You get the brown solution when you try and oxidize the cobalt with 6NH3 with a 2 plus into the cobalt with 6NH3 and 3 plus. I actually don't know the color of this cobalt 3 plus aqueous solution, but I know you will oxidize the cobalt 2 to cobalt 3 using the oxidizing agent. In the presence of excess NH3, you're gonna get cobalt NH3 6, 2 plus. And that, just like what I said, when you add in the hydrogen peroxide, it does go to like brown or much darker brown kind of color. So it's quite a disgusting color, unlike the very nice color that we usually see with transition metal complexes. They're not asking for color here because these are associated with the chromium compound. But thinking about the relationship between what happened there, we can deduce the formula of the associated chromium compound. But be careful, these are cobalt 2 complexes. We are dealing with chromium with 6 water, and we have a 3 plus there. So our formula of our hydroxide will be chromium with 3 hydroxide, because it cancels out the charges of the 3 plus on the chromium. And this is a precipitation reaction, because what we are doing is we are precipitating out the chromium 3 hydroxide. Back in year 9, you will be expected to write half equation. Sorry, not half equation. What am I talking about? Ionic equation. So chromium 3 plus, which of course is actually chromium H2O 6, and then 3 plus. So there's your aqueous. I'll add in 3 aqueous hydroxide ion, and I'll kick out chromium hydroxide as your precipitate, as your solid. And then I'll also kick out the 6H2O. So this is ionic equation for that precipitation reaction there. Okay, so to the next one, which is H2O2 aqueous. So this will be, it could be an oxidizing or reducing agent in the context of chromium 3 plus. So we know that will actually go to chromium 6 plus. If you look at the E naught value, so chromium plus 3 in the chromium 3 plus aqueous, if you want to go to a higher oxidation state of which it is stable one, you just have to look in the data booklet. You don't have chromium 4, you don't have chromium 5, you have chromium 6. And examples of chromium 6 you will have come across as Cr2O72 minus, which is your orange color. But of course, they are in equilibrium depending on the acidic or the alkaline conditions that you have. With this chromate 6, this is also chromium plus 6, but this is yellow in color. This is called chromate 6, whereas the other one is called dichromate 6. Okay, you might not have seen the equation before, or you might have. Pardon me, I might actually get this wrong the first time, but let me just try and write the equation first. So it's a very common equilibrium questions with Le Chatelier principle in AS. So I got 2 chromium, I got 8 oxygen, I got 7, which means the H plus is on the right hand side, and I have H2O on the left hand side. That way I just have like that, and I've got the 7 plus 1, 8 oxygen. I've got the 2 hydrogen, I got the 2 chromium. So this equation is a balanced equilibrium now. So this is your yellow color on the right, this is your orange color on the left. This is a very common question. Is it a redox or is it not a redox? Back in S, they can ask you in terms of Le Chatelier principle, the color changes as you add in more acid. As you change the acid, all acid contain H plus, so it shouldn't affect the color distribution at all, and all acid will do the job because all acid contain H plus. The other question they can ask is what happened when you add in hydroxide. Hydroxide can change H plus, and therefore they can change this concentration of H plus. As they neutralize the H plus, they can make this equilibrium shift to one side, and therefore you can get different color. Anyway, going back to the species of the chromium that you're going to get, has to be chromium plus 6, so you can get Cr2O72 minus, which is dichromate 6. If you want, if you know your other chemistry, you can write down Cr042 minus as well, but I will bet that Cr2O72 minus is probably something that you are very familiar with. It is actually the oxidation of the chromium species from chromium plus 3 to chromium plus 6. But it's a reduction of this species. So instead of writing oxidation, I am happier to write redox because you have a partner in oxidation, chromium plus 3 to chromium plus 6, and then you have the H2O2 that undergo reduction. I haven't shown you where to get a chromium plus 6, but I hope you know where to get it. Maybe I should quickly just show it. Chromium plus 6 oxidation state. So if you have Cr2O72 minus, don't know why I write it down, minus 2 overall charge, 2 chromium plus 7 times minus 2. The oxidation state of each oxygen, the compound is minus 2, so 2 chromium is plus 12, each chromium is plus 6. For the Cr042 minus, the charge is minus 2, so that's the overall oxidation state. Chromium plus 4 times minus 2, chromium is going to be plus 6 there as well. No change in redox, no change in oxidation number. This is not a redox equation. Moving on to the very last part of this question. So you have excess of NH3. With a little bit of NH3, it's going to behave just like hydroxides because NH3 is a base. So initially you get a precipitate of chromium 3 hydroxide. Just like with the cobalt, with a little bit of NH3, you initially get this blue precipitate. When you add in excess NH3, you get this brown solution forming. Essentially what we have is going to be this cobalt. Oh, sorry, not cobalt, because we are not talking about cobalt chemistry. Chromium with, not H2O, but NH3. It's going to be a complete substitution, so 6 of them. And then this one will have a charge, because this thing has no charge as a ligand. This is not a redox reaction. It's just substituting the H2O, the 6 H2O with 6 NH3. So I still maintain the 3 plus charge, which I have got in my chromium 3 plus aqueous solution, which by the way is green. So that is what you call chromium 3 plus aqueous, and that is the color you get when your dichromate 6 act as oxidizing agent. They go from orange to green. This is the green color of that aqueous chromium 3 plus. So that is just your classic ligand substitution reactions because you're just substituting one ligand with another. and this ligand is the same as H2O in the sense that they are both uncharged, zero charge ligand there. Question 1, part C, is basically this idea of it's not really our fixed essay. This is slightly different, but they are talking about why different ligands, different colors. So it's not really about the origin of colors. It's more about why are there different colors when you have chromium H2O6 with the 3 plus versus this chromium 2 O2CCH3. What is this thing here? But anyway, doesn't matter. So why? Okay, the two complexes have different ligands, have different number of H2O ligands. So on the left you have 6 H2O, on the right you just have 2 H2O. So overall, different ligand set. Different ligand set meaning different combinations of ligands in the complexes. We know that the d orbitals actually get split, as you know, in the presence of ligand. The d orbitals get split like that in the octahedral complex, whereas they don't get split without any ligand at all, without ligand. And this splitting is separated by delta E equal to HF equal to HC over lambda absorb. And they can only absorb in the visible light region, and therefore whatever color that you see has to be the combination of the colors that are not being absorbed. So the fact that we do get splitting is a result of the repulsion of the ligand and the d orbitals that contain the electrons. So they repel differently, giving you different energy gap. So therefore this ligand, different ligand sets, therefore different repulsion between ligands and the electrons in the d orbitals. Therefore different delta E equal to HF equal to HC over lambda absorb. That means different lambda absorb for the visible light. If you absorb different lambda, if you absorb different wavelength of the visible light, therefore we see different complementary color. So different complementary color. So this is a very very much waffling, but you know it still need to involve the right concept, different complementary colors observed. So it's just about the different delta E. I think it is the main concept there. They're not even asking you to draw this splitting diagram or whatever. But for that 2 marks, I would say the idea is different ligands, different repulsions, different delta E, different lambda absorb, different complementary color absorb there. Okay. Question 1, part D. So we are given this thing here. So they purposely, well, they went away and tell you water and ethanoate ions behave as different type of ligand. So H2O is a monodentate ligand. Monodentate ligand means they only form one dative covalent bond per water molecule, only forming one dative covalent bond per ligand molecule. So per ligand. Ethanoate ion, which is basically CH3CO2 minus, like that. So they have got 2 sides there. So first side is on this oxygen, but these electrons can get delocalized over the carbon sp2 framework there. So ethanoate ion acts as a bidentate ligand. Bidentate ligand basically means they can form 2 dative covalent bonds per ligand, forming 2 dative covalent bonds per ligand, and this is not ligand molecule per ligand ion there, because ethanoate ion is an ion. Now deduce the coordination number of chromium and the geometry in this structure. So the structure they have given you is like that, and then they have got the OH2 there, and they have shown this is pointing out and this is pointing away from you behind the screen. And I've got O and O there. There is 1, there is 2, and then if I just draw there on top and on top like that, there's 3, and below there is 4. Okay, so I have 4 of this ethanoate ions, and I want the coordination number. So first of all, coordination number refers to the total number of covalent bonds. Total number of dative covalent bonds. Coordination number is the total number of dative covalent bonds around a metal center. So I have 1, 2, 3, 4, 5, 6. I have an octahedral environment. So 6 dative covalent bonds around my 1 chromium center. My geometry is octahedral. My bond angle is 90 degrees for each of these things there. What is the type of bond between the chromium? So that is going to be a covalent bond. So it's quite rare that you think about metal forming covalent bond, but in this case, each of these is a dative covalent bond. So this has got to be a covalent bond being shown as such there. So there's just covalent bond between the chromium atom there. So question 1, part E. So we're going to construct an equation. So this is a little bit of electrochemistry. We have Cr2 plus oxidized to Cr3 plus. So we have Cr2 plus aqueous going to Cr3 plus aqueous. That is based on the question. And in doing so, this chromium plus 2 to chromium plus 3. So I must lose electrons. That is my oxidation. From your O-level IGCSE chemistry, there was an acronym. Oxidation is losing of electrons. Reduction is gaining electrons. So I've lost electrons. I have the electrons on the right hand side from the lower oxidation state to the higher oxidation state. So I react with oxygen. So I need to find something where the oxygen undergoes reduction. So oxygen is to gain electrons. I found it in the data booklet. O2 plus 4H plus 4 electrons going to 2H2O, and this is my reduction. So I just write oxidation there, and this reduction because it's gaining of electron, the other one is loss of electrons. If I just write down the E naught, basically the standard reduction potentials for the second one is plus 1.23 volt. And for the first one, it's obviously being shown as reduction potential. So you're looking for chromium 3 plus going to chromium 2 plus. So there's minus 0.41 volt. This is as given in the data booklet. It's shown for the reduction, which is going this way, chromium 3 plus plus electron going to chromium 2 plus. But we have identified that as our oxidation. So this is our E-ox and this is our E-red. So going back to your thing there, they want you to write an ionic equation. So we need to write where the changes in oxidation number get balanced out. This is 4 electron, this is 1 electron. Lowest common multiple, primary school mathematics, says that you must come up with a common factor there. So common factor there is 4. So multiply this whole thing by 4. Then you're going to get 4, 4, and 4. The 4 electrons on the right cancel the 4 electrons on the left. But what you get is O2 plus 4H plus, and then you have 4Cr2 plus going to 4Cr3 plus 2H2O. They come from this balance equation, which we have gotten straight from the data booklet. We've done our multiple of 4 correctly. The 4 electrons cancel out, so everything should just balance out. O2 to oxygen, 4 hydrogen, 4 hydrogen, 4 chromium, 4 chromium, plus 4. And then plus 8 is plus 12, plus 3 times 4 is plus 12. This equation is definitely correct. Last but not least, they want us to do in part 2, calculate the E cell for this reaction. E cell is E red minus E ox. So this minus already take into account that the E ox is the opposite step. So this is what we have written down straight from the data booklet. It was shown for the reduction potential. I identify this as my EOX already. I do not change the sign whatsoever. I just do my E right, plus 1.23 minus, and then minus 0.41. As I said, I do not change the sign. I just take it as it is from the reduction potential, showing the reduction from the data booklet. And ultimately, I put that into my calculator, 1.23 minus 0.41 negative. I get 1.64 in my calculator. That would be wrong, because as with anything physical chemistry, sign, value, and unit are very, very important. And as you could see, this is greater than 0. So the E cell is greater than 0. So this is feasible, and this is spontaneous reaction, and this will happen. That's why chromium 2 plus aqueous will get oxidized in air to chromium 3 plus, which will give you the green coloration if you just leave it in air naturally. That's the end of that 15 mark first question on transition metal chemistry. Question 2 is a fixed asset that you will have seen in many of my topical playlists. It's basically asking you to think about the thermal stability of group 2 nitrate. We know that the group 2 nitrate essentially, well, they wanted us to write a question afterwards anyway, so I'll just write it to show you what it forms first. So I give you the group 2 oxide, which is M2 plus and O2 minus. It give you 2 NO2 and it give you half O2. I've done this equation a lot of times that I know it balances out this way. If you want, you could multiply by 2, you get 2, 2, 4, and 1. So the ratio of NO2 to O2 is 4:1. They want us to state and explain the trend. I typically like to explain first. Essentially how you explain it is down group 2. So down group 2, there are more filled inner shell. So as a result of it, your size of cations, so the ionic radius of the cations, the M2 plus increases. When your radius of cation increases, M2 plus become, well, the charge density will decrease. Charge density of M2 plus decreases as the ions remain plus 2. Still plus 2 charge. So size has increased, but plus 2 charge is still the same. Therefore, the charge density decrease. M2 plus cations become less polarizing. So the cation is polarizing, it becomes less polarizing on the NO3 minus ions. So therefore, the NO covalent bond is less weakened. So you are not weakening it that much. Therefore, more difficult to decompose, since it requires a lot more energy to break that NO bond, since it's not very polarized by the cation. So more difficult to decompose. And if it is more difficult to decompose, what I can say is it becomes more stable to heat. So the thermal stability of the group 2 nitrate would increase. They become more stable to heat as they are more and more difficult to decompose. Question 2, part B1. This is basically asking you to do the exact same equation as I've done above. So lead 2 nitrate decomposes the same way as group 2 nitrate. They'll give you lead 2 oxide, Pb2 plus O2 minus. They'll give you NO2 and they'll give you O2. 2 of the nitrate will give you 2 of the NO2. When you count the oxygens, there are 6 oxygen atoms on the left. Here you've got 1, here you got 4. 4 plus 1 is 5. You want 6 altogether on the right. So this is oxygen molecule, so you need a half there. They don't ask for stat symbols, but this would be a solid, giant ionic structure. This as well, solid, solid. This is a brown gas, and this is a colorless gas, which you can't see obviously. Now they say how would the ease of decomposition compare with barium nitrate? You're supposed to use the data booklet. Based on the essay that we have written in part 1, we're supposed to compare ionic radius. So let me just go straight to the page on ionic radius. We are comparing ionic radius, so make sure you choose the right one. The ionic radius of Pb2 plus, I wonder if I'm given Pb2 plus at all. I am not given the Pb2 plus. Let me just double check again. Period 2, period 3, group 2, group 14. Yes, I am given it Pb2 plus under group 14. So the radius of Pb2 plus is 0.120 nanometer. This versus the radius of the barium 2 plus, as they're asking us to compare to the barium compound. There are two entries in barium in the group 2. Make sure you choose the one with the Ba2 plus because we are comparing ionic radius. Okay, so be careful based on the essay that you have written previously. So going back to the original question, so Pb2 plus is smaller, so it's got smaller ionic radius than Ba2 plus. I've already used my data booklet and quoted the values for the ionic radius. Therefore, this thing is more polarizing. They are not, oh, they do ask you to explain your answer. So Pb2 plus is more polarizing than Ba2 plus. Polarizing is on the nitrate. So if it is more polarizing than the nitrate, therefore PbNO3 twice is easier to decompose, because based on the previous essay, if you are more polarizing on the anions, the NO bond is more weakened, so the lead to nitrate is more easier to decompose than the barium nitrate by using the data booklet. Next up, question 2, C part 1. We have barium ethane dioate, which comes from ethane dioic acid. So this is Ba2 plus C2O4 2 minus, and it decomposes to give you barium oxide and a mixture of two different gas. So obviously you don't get NO2 here because there's no nitrogen to begin with. We get two different gas. They are not telling us what gas it is, but they are different gas. I imagined it would be carbon dioxide, but then if I just produce carbon dioxide, my oxygen doesn't balance out, and I can get oxygen, but I'll get too many oxygen on the right side. So I think actually it could be O2 actually, because then you have one barium and one barium, two carbon, one carbon. Oh yep, carbon doesn't make sense there, so it can't be anything without carbon, because the moment I put 2 there, I have 4 plus 1, which is more oxygen than what I need. So I cannot have 2 CO2, I must have 1 CO2, but this leaves me 1 extra carbon here. So different gas. Carbon as a solid is graphite diamond, so it can't be carbon. As a gas, it could be carbon monoxide. 1 barium, 2 carbon, 1 and 1, 2 carbon. Oxygen, 2, 3, and 4. I've got 4 oxygen. I think this equation is balanced now. All right. Question 2, C part 2. So I have a bunch of these. It's a percentage by mass question. It's a percentage composition by mass. So it's not related to the equation I've written before. So redox reaction takes place, all the barium ethane dioate reacts, and what is happening here is let's see what's going on. Redox reaction, blah 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 blah. So first of all, you have barium ethane dioate, and then you react it with MnO4 minus acidified. A redox reaction takes place and all the barium C2O4 reacts, and then this thing is with excess of this, so and then you will have unreacted MnO4 minus, and it is this thing that you do another titration plus iron 2 plus aqueous. This is an oxidizing agent, so any remaining bit of it can oxidize iron 2 to iron 3. So we have two redox equation here. So let's start from the very end. So your first equation is going to be MnO4 minus plus 8H plus there are 5 electrons involved, so I need 5 Fe2 plus, because then that will give me 5 Fe3 plus, and they'll give me another 5 electrons on the right side from the third equation that's shown in the on your question paper, which you know where to find obviously without me telling you to, and this will give you Mn2 plus 4H2O. What I've done is I've combined to give you the full equation by multiplying the iron 2 and iron 3 equation by 5, and you get 5 electrons on the right. They will cancel the 5 electrons on the left for the reduction of the manganese plus 7 to manganese plus 2. From there, I can work out my mole ratio. So what do I want? I want the mole of the MnO4 minus is to the mole of the iron 2 plus, and I have 1 mole of iron 2 plus reacting with 5 mole of iron 2 plus from the balance equation. And what do I get? I get at the bottom, I have the volume of the iron 2 plus, which is 30.40 cm cube. I do it in dm cube by multiplying by 10 to the minus 3, because n equals to CV, the concentration is in mole per dm cube, so your volume of solution must be dm cube. I don't have this information on the manganate, and in fact that is what I want to find. This is how much manganate remains at the end of the reaction unreacted. Okay, so the mole of the manganate unreacted in the first reaction, unreacted from first reaction, is going to be equal to, just bring up all that thing, 1 over 5 times 30.40 times 10 to the minus 3 times 0.0500. Press that onto your calculator. Oops. And I get 3.04 times 10 to the power minus 4 mole. Anyway, so what other information am I given? I was told how much manganate I use in total. In total, which is in excess, I have 50.0 cm cube, but I also have 0.0200 mole per dm cube. So the mole of the KMnO4 reacted in the first reaction is going to be the total KMnO4 that I react, which is 50.0 times 10 to the minus 3 dm cube times 0.200. This is how much I put in based on the question. This is in excess. How much MnO4 minus reacted in the first reaction is going to be this total minus how much remained. How much remained at the end of the reaction was what I did for my second titration. So this amount from the second titration was actually how much unreacted. Take that away from the total that you put in for the KMnO4, you're going to work out the mole of MnO4 minus reacted in the first reaction. So it's minus 3.04 times 10 to the power minus 4 mole. So that very first bit, 50.0 times 10 to the minus 3 times 0.02, I get 1 times 10 to the minus 3, and then minus that previous answer. Now I have 6.96 times 10 to the power minus 4 mole of KMnO4 that actually reacted in the first reaction. What else do I know in the first reaction? I know that in the first reaction, so it's KMnO4 reacting with manganate. If you compare the first two redox equation given, so C2O4 2 minus going to 2CO2 plus 2 electrons, MnO4 minus plus 8H plus 5 electrons, giving you Mn2 plus 4H2O. Without writing the whole balance equation, which I really don't need to, there are 2 electrons here, there are 5 electrons. I'm going to do lowest common multiple, which is a primary school mathematics. So LCM of 2 and 5 is actually 10. So you're going to multiply the top equation by 5 and the bottom one by 2, like that. And then you will get the mole of C2O4 2 minus is to the mole of MnO4 minus. So you're going to get 5 times ethane diovate ions, and then you're going to get 2 times MnO4 minus. Okay, so that's how I can get my mole ratio. And in my part 3, which I'm going to continue down there, I will just paste that. And this is how much reacted in the first reaction between the ethane diovate ion from the barium ethane diovate. I want to know the mass of the barium ethane diovate that reacts. Okay, so the mass, the mole of the BaC2O4 give you the C2O4 2 minus. So the mole of barium ethane diovate is the same as the mole of that. So the mole of that is going to be equal to the mole of barium ethane diovate. So what I can do is I can just sub this out, and I have BaC2O4 So I want the mass of barium ethane dioate in the pure sample. So I have the mass of barium C2O4 divided by the MR. So obviously I need the MR of BaC2O4, which is given very conveniently in the question, 225.3, so I don't need to waste time and do that. So that's my mole of barium ethane dioate on top. At the bottom is how much MnO4 minus reacted in the first reaction, which was what I did in my difference there. Total KMnO4 put in minus the KMnO4 left at the end of the reaction that you do titration with iron 2 plus. 6.96 times 10 to the minus 4 mole. 6.96 times 10 to the power minus 4 mole. So you can rearrange your equations. Before you press your calculator, you're going to bring that up. So you're going to get 5 over 2 times 6.96 times 10 to the power minus 4 times 225.3. And I got my final answer as 0.392022 gram. This is the mass of barium ethane dioate in the sample out of 0.5 grams. So the percentage of barium ethane dioate is basically 0.392022 out of 0.500 times 100%. So I got my final answer as 78.4044. I should run out my final answer to appropriate number of significant figure, which in this case is 3 significant figure. If you look at the mass given, 1 significant figure, 2, and then 3 significant figure. Of course, you could also give it to 4 sig fig, given that the titer given for the KMnO4 was 30.40 cm cubed, so 3 or 4 significant figure is entirely acceptable for that 4-mark question. The very last bit of this 12-mark question, so let me just think back. Was that question 2 or was that question 3? So that was question 2. We know that barium hydroxide, well, it says completely dissociated. We know typically the pH of barium hydroxide is around pH 14 because it's very, very soluble in water. It's a very strong base. So it's going to give us Ba2 plus and 2 OH minus based on the stoichiometry in this balance equation. So what you have is you have 0.120 mole per dm cube. So what happened then is 1 mole of these will give you 1 mole of that and 2 mole of that in the same volume. So this is just dissociating to that. Therefore 0.120 will give concentration of OH minus as 0.120 times 2, which is 0.240 mole per dm cube. So that's your first job. If your OH minus is 0.240, then we can work out Kw equal to 1 times 10 to the power minus 14 equal to H plus times OH minus. And I want to find my H plus concentration, so 1 times 10 to the power minus 14 divided by OH minus concentration, which is 0.240. So you might do it in a slightly different method, but you might realize that at the end of the day, you probably have the exact same method as mine. It's just in a different form. So once you get the concentration of H plus, pH equal to minus log 10 of H plus. So your previous answer, just take the log 10 and put a negative, and it's a sensible number. They don't tell you how many significant figure, but look at the data given. 1, 2, and 3 sig fig in the data given. 1, 2, and 3 sig fig in the data given. Back in topic 1 in AS chemistry, they did specify that candidates, A-level candidates, must know what is appropriate number of significant figure given the data and the precision of each particular question. Okay, so that's it for that 12-mark question. So question 3a part 1, they want you to define standard electrode potential. So standard electrode potential, or the way we pronounce this as E naught, is the potential difference. So you're looking at whatever your system is. So this is relative to a standard hydrogen electrode. So everything in the data booklet is referring relative to the standard hydrogen electrode, which has a relative value of 0.00 volt. So by default, this is between a standard hydrogen electrode and a metal. basically the electrode. In the case of a non-metal, you will have a metal as an electrode, which is typically platinum as your inert electrode, which is why it's between that and a metal, which is immersed in a solution, and this solution containing the ions. I don't want to say metal, I just want to say the containing the ions, and this is at 1.00 mole per dn cube concentration, 298 Kelvin or 25 degrees Celsius, and also 1 atm pressure. So these are the standard conditions as required by the definitions as part of that standard thing there. Anyway, so we have the next part of the questions. We have 3 redox systems. What do they want us to do? They want us to complete the table by adding the labels A, B, and C to deduce the order of E naught for the 3 half cells. How do we decide this? Okay, so looking at what you have, okay, so if I just very quickly scribble out what we have. Nope, I don't want that. Nope, I really don't want that. Okay, never mind. I'll just draw it like that and that, and then we have the salt bridge, and then obviously we have a platinum and a voltmeter going like that. We have a plus, we have a minus electrode there. What we have here is obviously it's a lot easier with your diagram in front of you, but obviously with the question paper not in front of me, the best I can do is show this in this context for you, and hopefully after I explain this first bit, then the second bit will be easy peasy lemon squeezy for you. So we're comparing the movement of electrons from one system of equilibrium containing the 2 complexes to the other one. Judging at this, if this is negative electrode and this is positive electrode, so what I can say is electrons are negatively charged, and it is electrons that are moving in a cell. So in a cell you have electrons moving. Electrons are negatively charged, they flow towards the positive terminal. Positive terminal is what you call anode. So electrons are coming, am I correct? Electrons are flowing here. This is the positive electron because the opposite charge there. So this is the anode. Okay. So this is the electrode at which you gain electrons. So reduction happen here. If reduction happens there, this means this is the E rad. So therefore we can say that this is more positive value, more positive E rad compares to this, because the electrons like to come here, and this is where reduction happened. So this goes from right to left. So this has more positive E naught. In your diagram, in your table that you're supposed to fill in for part 2, you're given it in terms of negative. So instead of thinking about more positive, I can think about it as less negative. Okay, so more positive means less negative. So let's say this is system number 1, this is system number 2. Then system number 1 is less negative than system number 2. Better don't use that numbering system. So what I have to do now is I can just complete these and paste it for the other system. Hopefully it will be clear for you as well. So let's see what we have on the other side. So what we have on the other side is something similar, but then we move these complexes around. So I have the En complex on that side. Instead of ammonia, I have water as my ligand on the left hand side now. This is still plus, this is still minus. So the electrons still like to move towards the positive terminal. So electrons go there. Electrons are negatively charged, they flow towards the positive terminal. Electrons like to come here because this is where reduction happened. So reduction happens here. Therefore, this is the E rad. Therefore, this is more positive or I can think about it being less negative. And if that is less negative, then the ruthenium, sorry, that should be En3, that should be En3 as well. Okay, so if that is the case there, so if this is less negative than that, and this is less negative than that, so ultimately we can fill in our table from the most negative to the least negative. We are just looking at redox system, redox system A, B, or C. So this thing here, this is redox system C, and this is redox system B, and this is redox system C, this is redox system A. So A is the least negative because it's less negative than that, and that is less negative than B. So the least negative is going to be A, and the most negative is going to be B. And C just lies somewhere in between, just like that. And there's 1 mark for a lot of explanations, but because they're not asking for explanations, it's just the way you think about it in terms of where the electrons are moving. The key really is based on these plus and minus given in the respective questions. So to the next part of this question, still on question A, but this is part 3. This is now stereoisomerism, and you have bidentate ligands, so you can just show them like that. What we have is we have ruthenium En3, 3 plus, so we have 3 times of the same bidentate ligand. This is the recipe for getting specifically optical isomerism. So they already told you it's stereoisomerism. They want you to name the type of isomerism. So the type is going to be optical isomerism there. And in terms of drawing it, I need to draw mirror images because there will be none superimposable. So I gotta draw 3-dimensional mirror images. I know that it's 3 times bidentate ligand, and they told me that I can draw it like that, and like that, and like that. So don't forget the charges in a square bracket. So that is just what I normally do. I don't know whether the examiner will penalize you or not, but it's a very common thing for transition metal chemists like myself. We always draw a bracket and then put a charge outside like that. So we have a mirror plane that we have to draw the mirror images of this thing. So before you draw mirror images, put in all the 6 coordination sites that you have in the octahedral complex. So these 2 are flat, just like these 2 are flat in the plane, in the screen or in the paper that you're writing on. These 2 are pointing away from you. These are 3-dimensional diagram, away from you, behind the screen, behind the paper. These 2 are coming up from the screen, from the paper, pointing towards you. So I put in all my nitrogen again. And I know this is a mirror image. I draw 1, so this will mirror project itself onto that side. So this project it onto here, this will project it onto there, and last but not least, this will project it onto the other side, like that. Okay. And of course, put in the charges as well, just as you would for the complex that you are drawing. So for the 3 marks, you get 1 mark there, 1 mark there, and 1 mark for being able to get its optical isomerism there. So question 3, part B. What do you have? You have a BR2 and BR minus. So if I write down these things straight from the data booklet, so you should be looking for alphabetical order. The way we write this is showing reduction, because everything in the data booklet is showing you reduction potential. Let me just open up my data booklet. So alphabetical order, the silver plus and silver, that is plus 0.80 volt. The bromine is plus 1.07 volt. So this is the more positive. This is the more positive E naught. Therefore, it is where reduction will happen. Where reduction happens means you will gain electrons here. Okay, so the electrons, the electrons come to this particular electrode. If I draw it, that means the electrons go from there to there. These are movement of electrons because reduction happens here, oxidation happens there. and if electrons come here, electrons are negatively charged, so this thing will be positive terminal and this thing will be negative terminal. You're not doing electrolysis. This is electrode cell potential, so E cell is going to be E red minus E ox, oops, not the other way around, E red minus E ox. So this method means I just need to read the value straight from the data booklet. The more positive one is the E red, so it's plus 1.07 minus bracket plus 0.80. Put it into the calculator. Oops, 1.07 minus 0.80. So your calculator will not show you the plus, but as with anything with physical chemistry, sign, value, and units is a must. Alright, as all the values given in the data booklet, they all have a plus when it's positive. Your calculator will not be able to think for you, so you need to think for yourself. So the direction of electron flow is going to go from the silver plus silver system towards the Br to Br minus system. As a result of what I've said earlier, you are not doing electrolysis. This is a result of cell potential. Now question 3b part 2. This is about changing to non-standard conditions. So far, everything you've done straight from the data booklet, those are all standard electrode potentials. So meaning all of them are under standard conditions. Meaning to say, originally, your E0 silver plus silver, which I have written above, it was plus 0.80 volt straight from your data booklet. So plus 0.80 volt is at 1.00 mole per dm cube. Let me just improve the handwriting a little bit. This is for silver plus electrons going to silver as shown in your data booklet. And we know that this was your EOX. It was your EOX just now. So that is your EOX. What can we say? Okay, it's better if I explain first because it will make more sense. This is basically a qualitative explanation in terms of Le-Chatelier principle based on this equilibrium. So for the Ag plus electrons going to Ag equilibrium, when you add water, when water is added, so you are diluting the concentration, so Ag plus falls below the standard 1.00 mole per dm cube. This is standard condition. So what happened then is the equilibrium will try to increase, to do the opposite. It will try to increase the concentration of Ag plus, because here the Ag plus concentration decrease, the equilibrium will shift in order to increase the concentration of Ag plus. The equilibrium will try to increase Ag plus by shifting to the left. When you shift more to the left, this E0 will become less positive. Therefore, it's no longer E0 because it's no longer under standard condition. So I don't write the E0 anymore. I just write E, Ag plus or Ag less positive, then plus 0.80 volt. And this is your EOX. So just now, if this becomes less positive, then this 1.07 minus something which is less positive, this will become more positive. So this one will become greater than plus 0.27. Therefore, E cell becomes more positive as you are taking away the EOX, which become less positive. So I don't really need to write this last statement. In fact, it was just a tick in the box. So it was less positive, it was no change, and the other one is more positive. So among the three changes, I will get more positive as a result of taking away something which becomes smaller. So as this thing becomes smaller, something positive minus something smaller, less positive, will become more positive. So this is just the idea on Nernst equation, but without really, writing down the expression for Nernst equation. This is the qualitative explanation based on Lee-Chatelier principle. Question 3, part C. They ask you to define the term ligand. So you always get free definition here and there. Ligands refers to molecules, or in fact it could be ions. Or ions, it must have at least one lone pair. You could have more than one lone pair of electrons, but you must have at least one lone pair of electrons. And what does this lone pair of electrons do? It forms dative covalent bond, or it forms coordinate bond, whichever one you like. Just stick with one, and this is to a metal ion center. Not necessarily metal ion, but most of the time it's metal ion. What we have is Kc. They are not asking for K step, so we have a Kc. And looking at the expression that you have the silver, and you have S2O3 twice. So there's two ligands on the silver plus, because each of these is S2O3 2 minus. So you got S2O3 2 minus, S2O3 2 minus, and you got one Ag plus, minus 4 plus 1 equal to minus 3. What am I talking about? That's how you get the minus 3 charge overall. Don't forget, this is how you write for the expression of a complex. For Kc, you need equilibrium concentration. So I put another square bracket for the concentration. The power is 1, because in front of the balance equation, which you have on your question paper, is just 1 of the silver. Okay, I think as a matter of fact, I might just write down the equation here, because it's quite an important thing to do this in the context of having the questions. So AgBr plus 2S2O3, 2 minus in equilibrium, giving you AgS2O3 twice, and then 3 minus, as I mentioned about the charges. What is important is also the stat symbol, because the stat symbol will govern you what will appear in the Kc expression or not. This is a solid, so concentration of unity is taken. Unity meaning concentration of just 1. The value is given as 1 rather than 0, so that you can still do the calculation whatsoever for the rest of your expressions instead of setting it to 0. So the top bit, they are both to the power of 1, but this bottom bit is to the power of 2. As you see in the balance equations, there are 2 S2O3 2 minus in the expression, so it's square there. And sometimes they ask for the units, but here obviously mole per dm cube times mole per dm cube is mole per dm cube 2 times, and you also have mole per dm cube 2 times. There's actually no unit for this particular expression. Question 3, C part 3. So we're given KSP and we are given K step. So we need to use these answers to calculate Kc for equilibrium 1 and include the units. So what do we know about K step? If we look at this expression, we can tell that K step, what am I looking at? K step as well as solubility products. Let's talk about solubility product first of all. So we have AgBr going to Ag plus aqueous plus Br minus aqueous. Okay, so that is your KSP. I should really draw an equilibrium. In terms of K step, it's relative to the aqueous complex. So what I have is 2S2O3 2 minus in equilibrium to give me AgS2O3 twice, Ag plus 1, and then minus 2 times 2 is minus 4. That's how I get it, it's 3 minus. Plus of course the water molecules that I kick out, so I'm not writing how many water molecules I have there. This is just a simplified expression to show for the what am I talking about for this second one, which is K step. So my KSP is equal to concentration of Ag plus time concentration of Br minus, both to the power of 1 according to this expression following the solubilizing the silver bromide like that. And from here our K step is going to be the concentration of AgS2O3 twice at 3 minus, don't forget concentration in the big square bracket, divided by the concentration of the Ag plus aqueous as well as S2O3 2 minus square. So use this answer to show what is going on. I have Ag plus there, I have Ag plus there. Obviously, you know, they are not going to be required somehow because there's no Ag plus concentration in there. So I need to try and relate these two together. I can see this thing is on top. So I also got Br minus on top. So it has to be K step times Ksp. Then the Ag plus and Ag plus cancel. I get this at the bottom. So I hope you can see that this is on top, this is on top. So K step must be on top and it has to be multiplied by Ksp since I want Br minus on top as well. It has to be this multiplied by that. So that's how easy it is to get the expressions. So Kc above, meaning this thing, is obtained by multiplying Ksp times K step. And you could see that because you know the definition for each of these. And based on this value, therefore, my Kc is equal to 5.4 times 10 to the power minus 13 times K step, which is 2.9 times 10 to the power 13. Include the units for Kc. Okay. So previously, I already told you about the units there. So it was mole per dm cube times mole per dm cube divided by mole per dm cube, the whole thing square. So obviously, you could see here that there are 2 lots of mole per dm cube and that cancel out the whole thing, and that's why you will not get any unit, and in your final answer you will just say no units. So let's do this on your calculator. So I get 15.66. However, given the data which was to two significant figure back in AS topic 1, they already said that candidate should be able to understand what is appropriate number of significant figure based on the data given. So this is Kc, I am giving it a 2 significant figure based on what is appropriate amount of data, what is appropriate significant figure based on the data given. Next up, so part D, which is the last 2 marks of this question. So question 3, part D, I have stability constant, and actually the previous K step was given, was it? Yep, because the AgS2O3 2 minus, so the whole complex is 3 minus. The K step value is given above as 2.9 times 10 to the 13, whereas silver with 2 Cn minus, and that is 5.3 times 10 to the 18. And next, last but not least, I have the silver diamine complex, which give me that. And deduce the relative concentration present in the resulting mixture. So hopefully not looking at the value in front, but rather looking at the powers of 10. This is 10 to the 7th. This is the smallest because it's 10 to the power 7th. This is the biggest, is 10 to the power of 18th. The bigger the K step, the more stable is the complex. The more stable is the complex, the more of these you will have in equilibrium. Therefore, in terms of highest concentration, you will have silver with the 2 Cn minus. So this is going to be highest, followed by the second highest, which is the silver with S2O3 2 minus, as given in the data above. And then this one is the smallest, comparing all 3. So silver with 2 ammonia and a plus. Now they ask you to explain, so you know, highest K step value would imply the more stable complex. Highest K step value implies AgCN twice minus is the most stable complex, and if it's the most stable complex out of the 3, therefore present in largest concentration. And having said that, the one with the smallest Cas depth will obviously be present in the smallest concentration, or in the question they said lowest concentration. That was how they label it. Okay, so that's the end of that 15-mark question number 3. Question 4. So we have here define the term lattice energy. So in Cambridge International 9701, lattice energy is defined as the enthalpy change. So it is an enthalpy change. It is to do with when 1 mole of an ionic solid, is formed from its gaseous ions. So we're talking about formation of ionic solid, which is why it has to be exothermic. Some other syllabus, depending on which curriculum you're looking at, you could be looking at lattice energy or dissociation. That is when you are breaking 1 mole of the ionic solid into the gaseous ions. Dissociation will be endothermic as a result of that. But don't worry too much about it. This is as stated by the Cambridge International and what we use. Part 2 of these questions, we want to find the enthalpy change of solution. Enthalpy change of solution means is the enthalpy change when I dissolve 1 mole of this substance in a large amount of water. So I dissolve it, I get Cu2 plus because this is copper 2 chloride based on the formula as you would know how to do from your year 9 chemistry. Anyway, so we're gonna have to relate it to lattice enthalpy. So lattice enthalpy based on the previous part is to do with gaseous ions. So I'm forming 1 mole of that ionic solid. So going up there, that is your lattice of that CuCl2. And then going up here, this is the hydration of Cu2 plus. And going up there, this is the hydration of Cl minus, but multiplied by 2 because I am hydrating 2 mole of these gaseous ions to give me 2 mole of these aqueous ions. What I want is this enthalpy of solution. Apart from lattice enthalpy, the rest of these, they are all AS level definitions from your chemical energetics topic. And in terms of using this Hess cycle going this way, enthalpy change of a reaction is independent, meaning it does not depend on the path you take as long as you start from the same point and end up at the same point. So what I have then is the enthalpy of solution is going to be minus the lattice enthalpy of formation plus the hydration of Cu2 plus 2 times the hydration of Cl minus. There's the Hess cycle there. Now I just need to put in the value. So minus the lattice, which is minus 2824. Don't forget it's minus lattice, so it's minus the negative value. Hydration of the Cu2 plus, always use bracket because you never know what could go wrong, so always use bracket. Now you're ready to press into your calculator. So minus negative 2824 plus minus 2099 plus 2 times 378 negative, I get altogether minus 31 kilojoule per mole, sign, value, and unit. This is question 3A part 3. So you're talking about the enthalpy of hydration of calcium 2 plus is minus 1579 kilojoule per mole. And then obviously given in the previous part of the question, the hydration enthalpy of copper 2 plus minus 2099 kilojoule per mole. So given that both are plus 2 charge, the only reasons why the hydration enthalpy is different must be due to the size, the ionic radius. So you say use the data booklet. So we gotta go to ionic radius. Make sure you look for ionic radius, basically the size of the ion and not the atom. So what do we see here? We have the radius of calcium 2 plus ion. So make sure you look for the right one, then make sure you got the units. The units are all in nanometer. It's stated in the table very clearly. the radius of copper 2 plus is part of transition metals. First row D block elements, Cu2 plus is 0.0773 nanometer. So in terms of the explanation, so both calcium 2 plus and copper 2 plus have the same +2 charge. We're going to be talking about charge density, so we need to relate to the fact that they both have the same charge. But actually, we cannot start a sentence with but, it's just grammatically wrong. So I'm just going to continue the sentence. But the radius of calcium 2 plus is equal to 0.099 nanometer, and the radius of Cu2 plus is equal to 0.073 nanometer. So charge density of Cu2 plus, which is charge over size, charge over volume. Volume depends on radius, so charge density of copper 2 plus is larger or is bigger than that of calcium 2 plus, therefore forms stronger ion dipole bond. This is straight from AS energetics on enthalpy of hydration, stronger ion dipole bond with water, therefore more exothermic enthalpy of hydration. Okay. Question 3, B part 1. So we're talking about electrolysis now. Electrolysis, we are using electricity to break up this thing called saturated. Saturated means it's a solution. Solution means it's in water. But then it is a concentrated solution because you dissolve it as much as possible. You learn this in O-level, so you got calcium 2 plus and Cl minus from the ionic compound. You also have H plus and OH minus from the aqueous component of water. So for the cations, it's a no-brainer. This is the one that will favor the oxidation. This means this will go to the, it's the H plus that will go to the cathode. I beg your pardon. Okay, so this one will be reduced at the cathode. But then between the anions, OH minus and Cl minus, because as a result of the concentration factor, then it's the Cl minus that will get oxidized at the anode and not the OH minus. Therefore, you don't get oxygen at the anode. Instead, you get chlorine at the anode, because you will get Cl minus going to Cl2 plus 2 electrons. Oxidation is loss of electrons, and obviously reduction is gain of electrons, so H plus electrons giving you H2, and I'm just balancing the equations. So in terms of what you get at the anode, you would get Cl2 gas, and in terms of what you get at the cathode, you will get hydrogen gas, H2. They say identify the substance. I just did. I don't need to give the name whatsoever. I can give the formula. B part 2, this is about an electrolysis calculation question. It's only 2 marks, so pretty direct there. Q is equal to IT, because this is charge equal to current in ampere multiplied by the time in seconds. So be careful there. The current is already in amperes. The time is given in minutes, so I have to convert it to second. So Q is equal to 0.75 times 60 times 60. I get 2700 coulomb. I like to label my steps like that. So that's the first step. Here, because they say you're using molten calcium chloride. If you're using molten calcium chloride, we're looking at the mass of calcium form. So obviously you are no longer producing hydrogen at the cathode, because in molten calcium chloride, you don't have any hydrogen ion present, no water, just the molten ionic compound. So that thing, plus 2 electrons, give you calcium. So pretty straightforward, is it? Nope, not that straightforward. I think I'm missing a step there. Let's see my step 2. This is the total coulomb that passed through. So 96,500 coulomb, which is 1 Faraday. So 1 Faraday is 96,500 coulomb is for 1 mole of electrons. So 2,700 coulomb is for how many moles of electrons? Well, it's going to give me this much mole of electrons. I'm not going to calculate that. I'll just use it as it is in the next part of the question. In the next part of the question, so obviously is finish up the calculation. So I have the mole of calcium because I want this thing, and I have the mole of electrons that actually passes through. So the mole of calcium is to the mole of electrons. From my balance equation, 1 mole of calcium comes from 2 mole of electrons. On the right hand side is the actual mole of calcium. So it's mass of calcium over the relative atomic mass, because mass of AR is the mole that I actually obtained based on the actual mole of the electrons that passes through. So altogether, I just need to rearrange my equation, do in 2 steps if you can't do in 1 step. Okay, so do in 2 steps. If you want to, I'm just going to bring up the denominator to the other side, and then I'll have mass over that, which I can bring up the 40.1 to the other side as well. And because this is equal, so I've just reversed the whole thing to the other side. 0.5, which is half, times 2700 divided by 96,500 times 40.1. I get quite a long answer, and 0.56098. And given the fact that 0.75 was given to 2 significant figure, 40.1 was given to 3 significant figure, I have a choice between 2 and 3 significant figure. To be appropriate, I think I would leave it to 3 significant figure, which means if I want to read to 3 sig fig, I look at this number 9, I will increase 1 there, and this is 3 significant figure. I forgot, was this question 3 or question 2? Actually, this was question 4. I must be wrong in the previous part when I labeled it question 3. Doesn't matter. Question 4C part 1. What is meant by entropy of a system? Entropy is a measure of disorder or randomness within a system. So fairly straightforward there. So the more disorder you have, the higher is the entropy. Looking at part 2, this is the change. When you have NaCl dissolving in water, what you have is you're going from the ions, which are tightly packed. So in the solid state, they are tightly packed, which is why the ions are not free to move. Therefore, you cannot conduct electricity in solid state, but you can conduct electricity in aqueous state because these are freely moving. So they haven't asked you to explain it there. They just ask you to think about whether it's negative, whether it's 0, or whether the entropy change is positive. Obviously, it's positive entropy change because when you dissolve in water, the ions become free to move around, and that's why you gain disorder. You become more random in terms of your motion. So that's for the first bit there. And for the second bit, what do we have? We have water solidifying to ice. Oops, what I meant is H2O liquid, which is water, going to H2O solid, which is gas. When you think about changes in state of matter, you can hopefully see that liquid has got a bit of space in between, and if I copy that and paste that, so this is about like very elementary changes of state, which you should have done when you were in year 9, and you revisited these when you were in lower 6, okay, meaning to say your first year of A-levels. So as you can see, they go from having a greater degree of freedom because they can slide past each other. There's the motion of liquid particles, to being tightly packed where they can only vibrate about fixed positions. So they lose that degree of freedom. So it's kind of opposite to this. Therefore, the entropy change is negative there. So they haven't asked for explanation there, but you never know when they will ask you for explanation in other cases. Part 3, evaporation of 1 mole of water. So we're talking about evaporation, 1 mole of water. Okay, so we have H2O liquid liquid going to H2O gas. So this is not necessarily boiling. It's only boiling if it happened at 100 degrees Celsius. This is at 25 degrees Celsius. That is why it's called evaporation, because evaporation can take place at any temperature. What do we know? We know that delta G is equal to plus 8.6 kilojoule at 25 degrees Celsius. So we want to see what happens between 25 degrees Celsius and 150 degrees Celsius. Okay. So what we know is that we know at 100 degrees Celsius we have the change of state. That is not just evaporation. We know that definitely there is boiling, and during that change of state we're going to get an equilibrium in the sense that the delta G will be equal to 0 as it crosses over from being a liquid to being a gas. So what happened is we also know that things evaporate, and evaporation of water is going to be a spontaneous process because it is feasible and it is spontaneous, as that's what happens when we dry our clothes or when we leave something to dry outside underneath the sun. In fact, puddle of water on the street or on outside on the road, it will dry up as a result of evaporation naturally. So what happened in this graph is we know that delta G will become more and more negative at higher temperature as it become more and more feasible. So what I'm doing is initially this is the provided value, and the temperature that we're going to start with is at 25 degrees Celsius as given in the graph there. So it says 25 degrees Celsius there, and it says this is negative and this is positive, and that is the exact value there. That is plus 8.6 kilojoule, and this value there is 100 degrees Celsius because at that particular temperature it's going to cross over to delta G equal to 0, which is on the y-axis there, and obviously it's getting more and more negative, and then it just becomes spontaneously feasible above 100 degrees Celsius because it's already boiled, so it just delta G just get more and more negative at higher temperature. But that's when it shift over from being we know it happens, but it's not happening on its own. So when I say feasible and spontaneous, what I mean is in the direction of increasing temperature. So there was I should have clarified myself there. In the direction of increasing temperature, it gets more and more spontaneous, upon which it crosses 100 degrees Celsius, then it becomes naturally feasible and spontaneous at all temperature above 100 degrees Celsius. Part D, sorry about that. So question 4D. So we have reaction of A and B is feasible at low temperature but not feasible at high temperature. So it's feasible at low temperature, and they say not feasible at high temperature. So what can we say about this? They say deduce the sign of delta H and delta S. So delta G equal to delta H minus T times delta S. So we are not being told that these are standard conditions, so we are not going to put in the standard conditions there. Regardless, we know that it becomes feasible at low temperature. So as temperature, if you think about it, feasible would mean delta G is lesser than 0, whereas not feasible would mean delta G is greater than 0. So as temperature increases, so there is high temperature, we want delta G to be positive. So the only way for it to be positive as temperature increase is if delta S is lesser than 0. So if delta S is negative, then minus T is positive, minus positive times negative will give you positive, and you want delta G to be greater than 0, so you want delta H to be greater than 0 as well. Okay, so in terms of the sign, the delta H is going to be positive, and the delta S is going to be negative. In terms of the explanation, I already explained it very hand-wavingly. Now we're going to put it into words. So as delta G is equal to delta H minus T times delta S, we can say we see delta H is greater than 0 as the forward reaction absorb heat. You think about temperature increasing, so it absorb heat. It is endothermic, and that is why it's becoming more and more feasible as temperature is that what we want? Not feasible. Oh yeah, it's getting less and less feasible at, let me get that straight. That is not right. That is not right at all. So I could get it for that, but that is not right for the delta H. I think delta H has to be negative there because of what happened here, because of what happened there. So that has to be negative because they say not feasible at high temperature. So meaning to say, if your forward reactions absorb heat, it will become more feasible at higher temperature. So this forward reaction actually releases heat. If you release heat in the forward reactions, you are exothermic. And when you release heat, so as temperature increases, system wants to release less heat. Therefore, favor the backward reaction. When you favor the backward reaction, it becomes less feasible in the forward reaction. Therefore, based on the information given, not feasible at high temperature, that's how I get it to be exothermic in the forward sense, is negative. In terms of the entropy, I would say if delta H is lesser than 0, for delta G to be greater than 0 as temperature increases, i.e. at high temperature, therefore the delta S has to be lesser than 0, so that minus T, which is going to be minus times positive, is going to be minus T times delta S is going to be greater than 0. Yeah, so that's essentially the reason why the delta S has to be lesser than 0 in order to make the minus T, which is negative times negative, will give you positive overall, and that's the only way for you to overcome the exothermicity of delta H based on this information given the question, and for the delta G to become greater than 0, to become positive at much higher temperature. Alright, so pretty tricky there. So that's the end of that 2-mark question to run up the 15 marks question number 4. Question number 5. So this start off as a fixed essay question. So for 4 marks, you are supposed to compare the basicity of phenylamine, so the NH2 bonded to a benzene ring. Then you compare with ethylamine, CH3, CH2, NH2, and you're supposed to compare with, this is a strange one, this is a 4-nitrophenylamine. So this is position 1, 2, 3, and 4. You could also think about 1, 2, 3, and 4. So these two are pretty common in the essay. So the other one being ammonia. So this thing is pretty new, but doesn't matter. So we can think of NO2 as an electron withdrawing group. You know it's an electron withdrawing group because you have it in your data booklet that it is actually 3 and 5 directing as part of what electron withdrawing group tends to direct substitution position onto. That's how you know it's electron withdrawing group. Anyway, basicity. What is basicity to do with? So I'm going to start by explaining first. So if I explain first, basicity is to do with how available is your lone pair on the nitrogen. Is the lone pair of electrons on the nitrogen to do what? To accept H+. Now if we think about phenylamine, well, this is also phenylamine, so we can compare a phenylamine system like that. So feel free to always draw some diagram in order to prove your point. So the lone pair there get delocalizes into the system. Lone pair on nitrogen in the phenylamine delocalizes into the benzene ring. Delocalizes into the benzene ring. For the nitro group, at position 4, this gets further delocalized. The lone pair gets further delocalized. The lone pair on the nitrogen of NH2 gets even more delocalized over the NO2 group, therefore less available, meaning to say the lone pair on the 4-nitrophenylamine is actually less available to accept H plus than just phenylamine. So far I've just drawn phenylamine on top there. What I'm gonna draw now is the effect of the nitro group. So hopefully it'll become clearer. So what I'm talking about is, if this is NH2 drawn like that, and you have NO2 group, which is actually drawn like this, the nitrogen with 4 covalent bonds, that's why it has a plus charge, and this oxygen with single covalent bond, that's why it's a minus charge. What happened is this lone pair can get delocalized. So if I draw the cocoon structure, I could delocalize it like that, and this could go there, and this could go here, and this could go there. So I can draw my resonance structure. Resonance is basically the different forms of these thing here. So when I form this double bond here, I become a plus. Obviously we don't like to destroy our aromaticity, meaning to say we don't like to have the benzene ring not being benzene ring. Overall, the plus 1 cancel the minus 1, the plus 1 plus 2 cancel the minus 2 charge. This is what you call resonance stabilization. Resonance stabilization is basically delocalization. Whereas previously, you could just delocalize the lone pair into the benzene ring. Here you have the nitro group at position 4, very conveniently set up, where all of these are actually these are trigonal planar. This is not exactly trigonal planar, it's trigonal pyramidal, but to some extent, the lone pair can actually get delocalized over the benzene ring as well as the nitro group. That's why I said here is this extra point, and this is probably what will catch out a lot of students who are just prepared for the most common essay. They don't think about what is the effect of the NO2 group, which is more electron withdrawing, and therefore it makes the lone pair on the nitrogen even more delocalized into the benzene ring via the NO2 group, and therefore it's actually less basic than just the phenylamine, which delocalized over the benzene ring only, whereas this it moved it further into the nitro group there. Of course, then you have to complete the essay by comparing ethylamine as well. So for ethylamine, the CH3CH2 group is electron donating by inductive effect. So that is electron donating by inductive effect. Inductive effect is something you have learned in alkene chemistry, in AS chemistry syllabus. If you don't believe me, you can have a look under alkene chemistry. That's the mention of this name. Inductive effect stabilizes carbocation, and here it's not stabilizing carbocation, but it's just pumping electron density to the nitrogen, and therefore making the lone pair more available to accept protons on the nitrogen, more available to accept protons, more available. Okay, therefore going back to your trend, if you want to think about the most basic, it is going to be the one where the lone pair is most available, which is going to be the ethylamine. So CH, well, I don't need a formula, just need to provide the name, I guess. Ethylamine, followed by phenylamine, and then followed by the for nitrophenylamine, which actually managed to delocalize the lone pair on the nitrogen even further into the nitro group, being an electron withdrawing, as I mentioned, via delocalization of the electrons. It's 4 marks because 1 mark for the trend, 3 marks for the explanation. Most students should be able to get these 2 correct. This is probably the harder one to explain unless you think about the structure and bonding of nitro group. Question 5, part B, is about synthesis. So this is the typical synthetic procedure. You're starting from the phenylamine for nitrophenylamine, and you're forming something which is Q, and then you get this last step where you get the azo dye. The azo dye consists of nitrogen-nitrogen double bond. Then you start it off from that phenylamine back bond, and you have like a phenolic group. Basically, you're doing a electrophilic substitution on a phenolic group. When you do a electrophilic substitution on a phenolic group, the phenol directs electrophilic substitutions at position 2, 4, and 6, or I can imagine as 2, 4, and 6, just like that. It could be there, it could also be there. This is what is given as R, so meaning to say what is going to be my Q. Well, I need it to be diazonium before I actually could do any diazotization. So this is the diazonium chloride, and to do this step 1, this is basically forming diazonium, and there is actually something that people call diazotization, and this thing is actually formation of azo dye. And to do the formation of azo dyes, you need to do electrophilic substitution, because that's what essentially happens. This is the mechanism for what happens when the phenolic group directs substitution on these positions and attack that nitrogen, giving you the 2 electrons back to that nitrogen with the positive charge. So all in all, you need your other reactant to be these phenolic substituents. So something that has the phenol back bond, and what you have done is you have substituted out these hydrogens with these nitrogen there. Okay, so deduce and draw the structure for Q. I have just done that. It's this diazonium chloride. Whatever you do, do not bond the chloride to the nitrogen, because the nitrogen there is a second period element. Even O-level or IGCSE year 9 students know that nitrogen, being a second period element, cannot have more than 8 electrons in the outer shell. Here we already have 4 covalent bonds with 8 electrons. You can't form 5 covalent bonds with elements from the second row of the periodic table. So part 2, so that was part 1. Part 2 of this question is reagent and conditions. So step 1, as I said, is forming the diazonium. To do that from the phenylamine, you would typically need dilute H or NO, which is nitrous acid. You could call it H or NO, or you could just call it HNO2. It's the same thing, and this has to be reacted with dilute HCl. They say reagent and conditions, so do not forget your conditions as well. This one has to be kept cold. 0 to 5 degrees Celsius is required to keep this thing. Anything above 10 degrees Celsius will be enough for the nitrogen to escape as nitrogen gas, meaning the whole thing would decompose. If you don't keep it as diazonium, you don't get the azo dyes forming. This is azo dyes. It will be brightly colored, whereas these things are not colored at all. Onto the step 2. Step 2 is basically forming this thing here. So funny story is, you know what's the funny story? Funny story is I've got to draw this in here, and they have given me a space there to write. I don't know why they give me the space there to write. Instead, what I'll do is I'll draw. I don't know how to write this as my reagent. This has to be the reagent, because that is where you direct the substitution. So it could be there, it could be there, but it decides to form this particular azo dyes at this position. Electrophilic substitution, loses the H there, kick out the Cl minus, you kick out HCl, but at the same time you get electrophilic substitution mechanism there. Okay, so when I say I don't know what to draw there, because they're giving me a written space, not too sure how to write that down in the written space, but if I were you, I would just draw. It's a lot easier to just draw. Okay, so that has to take place with that. And what happened is sometimes people use aqueous NaOH because they want to make the phenol a little bit more activated. You can deprotonate phenol and it will make the benzene system even more reactive towards electrophilic substitution. It will attack this much better. So you will warm up. You will warm from 0 degrees Celsius to room temperature. So as you warm it up slowly, basically you keep that thing stable. You keep this thing that was stable at 0 to 5 degrees Celsius or 0 to 10 degrees Celsius, and then as you put in the phenolic component in the presence of base, it's going to be highly activated. It attacks this particular electrophile on this nitrogen. In doing so, kick out that hydrogen there and kick out the steamy white film HCl, and you just let it warm up slowly from that low temperature to room temperature, which is 25 degrees Celsius, without heating whatsoever. Component C seems to be much longer question, but what do we have in component C? We started out from this thing called methyl benzene. So we have a methyl group on the benzene, and we have E, which we don't know what it is, and we have F, which we don't know what it is, and we have step 3, which we know what it is, but here we have NO2, here we have CO2H, and here we have Br. So what do we see here? We see that we have done a couple of things going from here to here. First of all, this is our methyl group. Now it becomes a carboxylic acid. We can think about oxidation of alkyl side chain on the benzene ring. So alkyl side chain of a benzene ring will get oxidized by acidified KMnO4 to give you benzoic acid. So alkyl side chain bonded to benzene. However, that is not the only reaction that's happening. We could also see there's nitration, which is a electrophilic substitution, not an oxidation, not a redox there. We also see another electrophilic substitution, which is Br. So there's bromination, halogenation. Don't forget that these are name of reactions, but the type itself is substitution, and the mechanism itself has a name. It's called electrophilic substitution mechanism. Should probably write it down somewhere so that you're not confused between what is type, which is what AS introductory organic chemistry we have taught you, and then this is, I can't even write properly, electrophilic substitution. Okay, so here in this question, the key is really the order of doing things. Do I want to oxidize first, or do I want to nitrate first, or do I want to brominate first? That's the important question. If you see carefully, the CH3 group directs substitution to position 2, 4, and 6, and this is given in the periodic table, which group do they direct on. If I oxidize first, if I do this first, then I'll get CO2H and like that, and that will direct to position 3 and 5. This is stated in the data booklet as well. The CO2H direct 3 and 5. I don't get any of my substituent at position 3 and 5 relative to the CO2H, meaning to say I do not want to convert to I do not want to oxidize first. That's my point. I do not want to do number 1 first. Instead, what I want to do is I probably want to do nitration first. So what I suggest is do nitration first. Then what happened is I will get the NO2 at position 2, and I still have the CH3 there. After that, what do? I don't want the benzoic acid first, because if I oxidize now, then I'll get substitution at position 3 relative to that, and this NO2 might also direct there. So I think the next best decision really is to direct it to position 4. So that is just to, based on the CH3 directing it to position 4, and the NO2 will direct to position 3 and position 5 relative to itself. If I go to green color, it will be the CH3 group that direct it to position that and position that and that, but that is already occupied, so instead it goes for these positions. So number 2 is going to be the halogenation there. Okay, so if I just copy paste that, so we're going to do the halogenation, the second bit there. So that is just Br, and then I'm going to do oxidation for the final step there. Hopefully that makes sense to you entirely. Let me just put that in the bracket. Does that work out all right? Yep, that looks all right. Let me put that in the bracket. Oops, nope, that doesn't look all right. Just make it a bit bigger. Nope, that doesn't look all right. Try that again. Yep, that looks better. So what we say is this is oxidation and this is electrophilic substitution. This is also electrophilic substitution. Now going back to the original question, they say give the systematic name of compound G. So this is the benzoic acid. This is the benzoic acid because it is a 1 carbon carboxylic acid bonded to a benzene ring. This is a nitro group. This is a bromo group. The benzoic acid is the number 1 important carbon there bonded to the benzene ring. So I've got 2 nitro and I've got 4 bromo. So in terms of the substituents, we want the one with the lower alphabet to come first. So it's 4 bromo and 2 nitro. In terms of the alphabet, B comes before N. So question 5, C part 1, the systematic name for G is going to be, what did I say just now? 4 bromo, 2 nitro, benzoic acid. For part 2, suggest the identities of E and also F, and we already did that based on the discussion about the order of substitution earlier. So what order of substitution matters because it's all about the directing effect, where you're going to put the substituents, and those are all information given in the data booklet. For part 3, so 2 is already shown above. And then for part 3, suggest reagents and condition for each of the step 1, 2, and 3. Well, actually, even though I put down these 2, 3, and 1, they are not the exact step as mentioned. The exact step given in the question is step 1, this is step 2, these are step 3. The one circle is basically what I've written down as the list of reactions that we have to do. So for this step 1, we have to do nitration of a methyl benzene. So for that we need concentrated nitric acid as well as concentrated H2SO4. And since we are nitrating benzene or methyl benzene or alkylated benzene, we need a reflux of 50 to 60 degrees Celsius to make it happen as well. For step 2, we are doing halogenation. We are trying to add bromine substitute bromine in place of the hydrogen on the benzene ring. So here we need acid catalyst. We use FeBr3 as your catalyst. Very important that you mention this. And then Br2 as your reactant. As a matter of fact, I should probably put catalyst before my reactant. So I need the Br2 as my reactant. I should probably mention that I need liquid bromine as my reactant and not aqueous bromine, because with anything in terms of benzene itself, you need a concentrated source of the halogens. What better than the liquid itself? FeBr3 catalyst. And again, electrophilic substitution on the benzene ring is not as easy as on activated phenol or phenylamine. Step 3 was the last step, which was the oxidation of the alkyl side chain of benzene ring. This one is very specific, has to be using the acidified KMnO4, or you can say acidified MnO4 minus, and don't forget to reflux it as well. So dichromate 6 will not work for this particular oxidation. That's the end of that 13 mark A2 aromatic chemistry. Question 6, this seems to be more on introductory organic chemistry. They're talking about, well, draw the skeletal. That's the first thing you can think about in the question. They want skeletal, finally. And they say C8H10, they want structural isomers. So they're not looking for stereo, they're just looking for structural isomers. So you should have circle or underline part of this thing, which they want you to do. There's also given information on carbon-13 NMR. So you're looking for how many different carbon are there. So we need to think about symmetry and number of carbon environments. How many carbon environments are there? So let's get started. C8H10, so all of them have benzene ring. Benzene ring is C6H6, but when they are substituted with something, they're going to be C6H5 when it gets substituted. My question now is C8H10. Could it be just like this? 6, 7, 8, 9, 10. So there will be C6H5 from the benzene ring, 6 carbon, 7, 8, 9, 10. So there's C10H, there's 5 hydrogen because one of it is substituted, 5 hydrogen, 6, 7, 8, 9, 10, 11, 12, 13, 14. So there's C10H14. I want C8, I beg your pardon, I want C8. So I need lesser carbon, 6 carbon, 7 and 8. So there should be C8H 5 hydrogens, 6, 7, 8, 9, 10. So I'm just looking for things like that. There is already one skeletal formula. So I don't know which order round it is yet, but let me try and draw all the possible isomers first. So I could have one carbon there and one carbon on the other position. I could also have what am I doing? I can just copy paste that because I'm working on screens. Very nice and easy working on screens, not so nice and easy for you, of course. Then what we do is we just put the methyl group somewhere else. I don't put it there because putting it there is the same as 1, 2, 3. So it's a 1, 3, which is the same as that. This is a 1, 3 position. It's a 1, 3 dimethyl benzene. And the other one is a 1, 4 dimethyl benzene. This is a 1, 2 dimethyl benzene. This is just what you call ethyl benzene. Okay, all of them are C8H10 obviously. So don't want to spend too much time on the name itself. Maybe not. Okay, let me just copy paste that and get the name right. Obviously there's not the right name yet. So there's 1, 1, 2, and this is 1, 4. Perhaps I can move it a little bit there to make myself some more space. Okay, so let's partition this so that it looks a bit clearer. Alright, so now having looked at these, we need to try and think about the number of carbon environments that are different. So here you can hopefully see there is a symmetry there. So everything here, this is different from this carbon here. So this carbon and this carbon is different. This carbon and this carbon is the same. They will appear the same signal due to symmetry. So I'm just highlighting the different carbons. So I have 1, 2, 3, 4, 5, 6. I have 6 times different carbon environment. Looking at this, I'm looking for 6 peaks in carbon NMR. So this must be isomer number 4. Okay, because it's got 6 peaks in the NMR, so this must be isomer number 4 there. See if that's better. Nope. So that line there can't be reversed. Oh no, I don't want that. I don't want the whole thing to be erased. Nope, I don't want that. Okay, that's much better. See if I can erase that. Okay, much better there. I should probably try and work on a okay, maybe I'll include in 1, 2, 3, 4, 5, 6. So 6 different carbon there. Okay, that way I don't have to erase for the rest. There's a mirror plane, but the mirror plane for this one is around there, meaning to say this carbon is the same as that carbon, this carbon is the same as that carbon, and then this carbon here is the same as that, and that carbon there is the same as this because of the mirror plane down in the middle. So 1, 2, 3, and 4. This is 4 times different carbon. And looking at the 4 peaks in the carbon NMR, so this must be isomer 2. Okay. Nah, I can't be bothered to erase that now. In terms of the mirror plane for the other one here, so it's there. So this thing is different from here because here you're next to something that is CH3. Here you have next to something which is just hydrogen. But this carbon here is the same as that due to symmetry. This and this is the same due to symmetry. This and this is the same due to symmetry. Oops, not pink but green. 1 2 3 4 5. So 5 times different carbon. So there's just isomer 3 there, leaving us with isomer 1 for the other one, because this one is the most symmetrical of all. If you think about that, and if you think about through the middle here, this and this, so altogether you have 1 and 2 and 3, because these and these are the same, these and these are the same, these and these and these and these are the same. So 1 2 3 environment. So altogether you just have 3 times different carbons environment, which is why this is going to be isomer 1 there. Okay, so I hope that makes sense for your 4 marks. Part B, so this is question 6, part B. So it looks like a synthesis question. You start from a benzene ring, not a problem. You have chlorine and then CH2, 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 and then COOH. So double check, ClCH2, 3 of them, and then CO2H. And you have it in the presence of AlCO3. This is your step 1. This is actually going to be a reaction, a name reaction. This is called Friedel-Crafts alkylation. That is the name of the reaction. It's not the type of reaction. Be very careful. The type of reaction is stated in the AS. The type of reaction is going to be substitution. And the mechanism, as stated in A2, is electrophilic substitution. I think a lot of students are confused when they think they know the name of the reaction. They thought it's the name of the mechanism or the type of the reaction, which is entirely wrong. So what happened with the AlCO3 and the Cl is this and this will form AlCl4 minus, and then you get a plus on the electrophile, such that you will get a plus there, and you will chop off this bit. So you get 1 2 3. So CH2, 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 and then a carboxylic acid there. Okay, so this must be W. If you double check, CH2, 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 and then the CO2H at the end there. Obviously then, what does that form? That gives you the acyl chloride. So if I just copy this, which means I don't have to redraw it, and then I convert the carboxylic acid at the end there to become acyl chloride. So this is basically using SOCl2, or you can use PCl5, or you can use PCl3Cl2. Those are your common reagents to convert carboxylic acid into acyl chloride. So that is your step 2 there, whereas previously that was your step 1 above. Okay. Obviously I run out of space now, so what I'm going to do is I will just copy all of these onto the next page. Nope, I don't want to copy, I want to cut it. And I'll just start afresh from here with a little bit more space so I can work down. And what I have in step 3, in step 3 I just add AlCl3, because then I have acyl chloride which will react with AlCl3 to give you acyl cation, because that, on the other hand, just now we have Friedel-Crafts alkylation for step 1. For step 2, what we have is we have Friedel-Crafts acylation. So Friedel-Crafts is the name of the, I think it was a duo who actually discovered this particular reaction. The type of reactions is still substitution. You are doing substitution on the benzene ring, and the mechanism is going to follow electrophilic substitution. So all of these things are basically in the syllabus as part of electrophilic substitution. So what's going to be my product? I'm going to get, actually what I can do is I can just paste this. Oh no, I don't want that. So what I'm going to get is actually the benzene ring, like that, and then I have a plus. What happens is the benzene ring can attack that, and loop onto itself. So what I have is 1, 2, 3. So I have just drawn part mechanism there. They are not asking for mechanism, they are just asking for the final product. There's a hydrogen there that you can kick out, and you kick out H plus, which will combine with the Cl minus that get released from the AlCl4 minus, such that you get plus HCl. But what will happen is 1, 2, 3, and then the fourth one goes there, and you will have another CO like that. So this is 1, 2, 3, and 4. This is going to be your final product. So I don't need okay, maybe I can put that on the side so that you can see what's going on, but that is obviously not what is required. What is required is your final answer, and that is the structure of X. X is equal to, well, they put in a bracket, X is C10 H10O. Be very careful. It is not another benzene ring. It's just another ring, but it hasn't got a benzene in it. And there are 6 carbon, 7, 8, 9, and 10. And there is 1, 2, 3, 4 hydrogen, 5, 6, 7, 8, 9, and 10 hydrogen, and 1 oxygen. So there's compound X there. Speaking of what I've done there, I talk about Friedel-Crafts alkylation. You will form AlCl4 minus and an alkyl cation. You will form AlCl4 minus and you get an acyl cation. So a difference between alkylation and acylation is kind of summarized in the next bit of the question. So this is B part 1. Write an equation for the formation of the electrophile. So you're going to use RCl plus AlCl3. What will happen is you're going to get R plus and you get AlCl4 minus. What happened at the end of the electrophilic substitution is a catalyst. So what happened is the H plus that you kick out plus the AlCl4 minus will then regenerate the AlCl3 catalyst, and that is regenerated or reformed because the catalyst is not used up in the reaction, and you get steamy white film, which of course is given out in the reaction. So all in all, I just will eliminate that equation because it's not being asked here. Deduce and draw the structure. That is done. And then number 3, suggest the reagent and condition for step 2. Step 2 was basically converting the carboxylic acid into acyl chloride. It's in the A2 acyl chloride topic. We can use SOCl2, PCl5. I'll just stick with SOCl2, but of course PCl5 will work. What is interesting is they also want the condition, so you gotta say the condition and not just the reactant, and you do this reaction at room temperature because they are very exothermic. In terms of the equation, so these are the extra thing from AS. When you have ROH, when you have SOCl2, the ROH will get converted to RCl. You will kick out SO2, you will kick out HCl. So you can imagine when you have carboxylic acid, you're going to do the exact same thing with the OH. Then you're going to get acyl chloride, which is RCOCl, and you will also kick out SO2, and you will also kick out HCl as well. So you see they are very similar. One thing you have learned in AS, and the other thing is A2, but in an A2 setting, they can ask you anything from AS in A2 paper because it's within their right to. The next question, part 4, is basically asking you to do the mechanism. This is the electrophile formed in B part 1. We are still using R plus that we already formed in the previous equation. So we start off from the benzene. You will know from my previous tutorials that instead of using the delocalized structure, I like to use the cocoon structure where I show the alternating double bond. But it does not mean that I don't know how to use this. I do. Instead of from the double bond, I use the electrons in the benzene ring, attack the carbocations. We know that this is the slow step because this is rate determining step as you lose aromaticity. Aromaticity is the stabilizing effect in a benzene ring. So when you lose it, it's always going to be slow. It's always going to take a lot of energy, very high activation energy. So if my R is there and I have a H there, I have a plus there. That is typically what I would do if I have alternating double bond like this. But here, I am trying to use the delocalized form. So what happened is this plus charge could get delocalized throughout, because this is actually a carbocation, a carbon with 3 bond pair and 0 lone pair. So this is sp2, 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 sp2. These are all planar. So essentially your charge could be delocalized over the carbon sp2, which are planar, but not on here, because this is now 109 degree carbon sp3 tetrahedral. So not only I can draw what I normally draw, I can also do what usually is shown in marking scheme. So I don't have to always follow one thing. I can do many things actually, but I do know what I'm doing, so that I'm not easily tricked or anything. What happens is I want to return to being aromatic, so I will lose the H, and it will get the electrons from the CH bond. Both the electrons go back into the ring. Whereas for my other form, where I show using double bond like this, from my double bonds, from my CH bond, the electrons go back to give me the double bond there. The alternating double bond is basically not the correct structure. The correct structure is the electrons get delocalized to give you that benzene ring. And then this is minus H plus. This is going to be fast with low activation energy, because you are restore aromaticity. You are restoring the stabilization due to being aromatic, and that's when you will kick out the H plus, which will take away the Cl minus, the AlCl4 minus that was formed from the catalyst, will react with the H plus to give you AlCl3 catalyst that will reform, because the catalyst is not used up in the reaction, and in the overall reaction you produce HCl as another product, steamy white film. Okay, draw the structure of the intermediate. So they do want you to draw the structure of the intermediate. Make sure it's a carbocation on that carbon there, and you want to restore the aromaticity and not do addition reaction. Instead, it's an overall substitution of this hydrogen on the benzene with this R group. That's the end of the 11 mark aromatic chemistry. Question 7 is about rate of reaction. So first bit of the question, what is order of reaction? So order of reaction is basically the power to which the concentration of a particular reactant, is raised to in the rate equation. And everything that is shown in the rate equation is involved in the rate determining step. So the power to which you raise it to is basically what you call the molecularity. Molecularity is basically how many molecules is involved in the rate determining step, which is the slowest step in the reaction. That's why they appear in the overall rate equation. Anyway, so this is question 7a part 2. Use the data in the table. So we're given a couple of data. I find it more handy if I actually have to copy down the data, because otherwise it really doesn't make sense at all if I just talk about it without copying this data. Obviously it's more tedious, but then without having to show on the actual paper, I think this is well, this is the next to best option really. So I mean, this is what we'll do with the with issues regarding the copyright things. So I don't want to land myself in problem again. So let's just stick with this. Doesn't matter. What is important is how we think about it. All right. So use the data in the table. So there's my data. Let me just move up a little bit so that we can have all the space we need. So there's that. And there's that. Oops, no, there's not a straight line. That's better. This is also better. Okay, move that down a little bit. Now that's better. Okay, so what do we know? We can see that. So at the moment, let the rate be rate constant, ClO2 to the power of A and OH minus to the power of B. If I compare, explain your reasonings for 2 marks. So compare experiment 1 and 2. If I compare experiment 1 and 2, you can see that ClO2 is constant. The concentration of ClO2 doesn't change. As the OH minus increases by how many factor? Increases by a factor of 4, obviously you can see 0.120 divided by 0.030, increases by factor of 4, as I'll show you right now. What happened to the rate? The initial rate also increases, as you could see, 10 to the minus 4 to 10 to the minus 3 by a factor of, well, you can show it on your calculator. This is just how you would explain it in terms of calculation. I get exactly 4 as well. So when I increase concentration by 4, I get the rate increasing by 4. So therefore, first order with respect to whatever is changing, and that is OH minus. So meaning to say B is equal to 1 because B is the order with respect to OH minus. Now compare the other ones. Just now I saw that, was it, let me see. So 0.30 in green and 0.030. So I'm going to go from 1 and 3. As the ClO2 minus ClO2 concentration increases, when the OH minus concentration increases, the rate again changes. So meaning it cannot be zero order. So compare experiment 1 and 3. When the OH minus is constant, can't even write constant properly, and the ClO2 increases by a factor of 0.050 divided by 0.020, 0.050 over 0.020. I think that is a factor of 2.5. Yeah. The rate increases also by a factor of 4.50 times 10 to the minus 3. Let me just write it down because I don't want to keep on referring to the table. Okay, so you can pop that into your calculator. And I get 6.25. So this looks like 2.5 square exactly, and therefore the order, therefore second order with respect to the ClO2, which is changing. So A, because A was the order I put in the right equation, so A is going to be 2, not 1. Don't know why I did 1 there. So 6.25 just now, this thing is equal to 2.5 square. That was what happened when I increase the concentration at 2.5. The rate increases by a factor of that square because its second order is ClO2 to the power of 2. So the number A there is 2 there. Okay, so for that 2 marks, you should be able to do it pretty quickly, and which is why the next bit, question 7, A part 3, they want you to write the red equation. Based on the previous question, you have ClO2 to the power of 2, and then OH minus to the power of 1 there. Now, very common type of question, use your red equation and the data from experiment 1. So if you look at the questions, your data from experiment 1, before you do that, it's best if you rearrange your equation first, because there is the essence of mathematics instead of having to write it again and again. So our rate for experiment 1 is 7.20 times 10 to the minus 4 divided by the concentration of ClO2, and you have to square it because that was the order with respect to ClO2, and then I take the concentration of OH minus 0.030. So I'm gonna cut that, and we can do the calculations down there. Cut that, and we'll do the calculation down there. Okay, so 7.20 times 10 to the minus 4 divided by 0.020 square divided by 0.030. I get 60, but don't forget your rate has a unit. Your rate has a unit of mole per dm cube per minute in the table given for free. Okay, your concentration has mole per dm cube square, and then you have another mole per dm cube from the OH minus concentrations. Hopefully you can see the mole per dm cube and mole per dm cube cancel out, and you get minute minus 1 over mole square dm minus 6. And of course that is not how you leave your final answer. You gotta express it in the simplified form, all in one line. So this looks better now. Mole minus 2 dm plus 6 minute minus 1. The unit of a red constant has no meaning whatsoever because it follows the red equation, of which, whatever appears in the red equation with a certain powers, it appears like that. This is divided by that, so it's got mole minus 2. This is minus 6. When you have 1 over that, it becomes dm to the power 6. Minute minus 1 remains. It's not second minus 1, so be very careful. Always read your table very carefully. You get 1 mark for the unit. Part B. So question 7 part B is basically working with the graph, but it's talking about decomposition of the benzene diazonium. Remember earlier there was a question on organic chemistry. Benzene diazonium reacts with a large amount of water. You are going to get phenol, and you are going to get HCl, and you're going to get N2 as a gas. This HCl will dissolve in water, and this is a product that is soluble in water as well. Phenol is weakly acidic. They can mix with the HCl, no problem at all. The N2 will just escape as a gas as you warm this up to room temperature. They said draw the structure of the organic product. I have done the full balance equations, but the answer, the organic product is definitely just phenol. So you just need to draw the phenol. My phenol is really ugly, so let me try that again. Still pretty ugly, but anyway, I'll live with it. That was B part 1. Question 7, B part 2. I find it hard for me to do this question without having the graph, so I'll stop recording and I'll copy the graph from the actual question. So I'm back with this graph from the actual question paper. Don't ask me where I get it from. This could be just any graph that I can draw on Excel, obviously. Use the graph to determine the rate of reaction at 100 seconds. So you want it at 100 seconds, and you want the rate of reaction at 100 seconds. This is a curve, so what you need to do is you need to draw a tangent at 100 seconds. It's a lot easier to draw it on a screen iPad because, well, in reality, you just need a ruler and you can get a tangent at that point, which is 100 seconds. So this is at 0, 0. So I just need to read the amount in y, the change in y over the change in x. So the change in y then, this is 0 0.015, 0 0.016, 0 0.017. So there is 0 0.0175. So 0 0.0175 minus 0, y2 minus y1. x2 minus x1, so this is 210, oops, sorry, no, 200, 300, so it's 220, 240, 260, 280, 290. So this is 290 seconds. So 290 minus 0, this is second at the bottom. On top is mole per dm cube. So altogether, what you get is 0.0175 divided by 290. These are given to two significant figures, so it's wise if I give my final answer to two significant figures, 6.0 times 10 to the power minus 5. Don't forget unit, mole per dm cube per second. This is two significant figure for that 1 mark there. Question 7, part C. You want to sketch a concentration time graph for a zero order reaction. Zero order reaction. What does zero order means? It means that rate constant multiplied by something is zero order like that. It means rate is just like that. But that is rate relative to concentration. This is rate against concentration will just be that. But what does that mean in terms of concentration against time? The reactant is still used up. But it will be at a constant rate. Okay, meaning to say it will be a straight line plot with a gradient of K. Okay, so this is concentration and this is time. Is my graph a bit straight? Yeah, it's all right. My graph is a bit distorted. Let me try and draw that again. So I think it's still distorted. Anyway, doesn't matter. Okay, so concentration against time, what we'll get is we'll get a straight line plot like this. A straight line plot has a gradient which is constant, and this gradient which is constant throughout is going to be K, because the gradient which is constant gives me the rate. As you know, zero order reactions, the rate is just K. Constant gradient for concentration against time graph for a zero order reaction. Now use your graph to suggest how the successive half-life vary as the concentration decreases. Okay, let's talk about half-life. So if this is what you begin with, half of the concentration is roughly there. So, you know, that is going to be the time taken. There's going to be the time taken for the concentration, initial concentrations to half. Then I'm going to half it again. Half from the green point. Hopefully you can see that, you know, the concentrations going half there, the time there is not longer the same. In fact, it's getting smaller. If you don't believe me, I can go half again. So now you can see the black one is getting a lot smaller. So this is the third half-life. The one in pink was the second half-life. The one in green was the first half-life. Oops, I don't want to write first half-life, I just want to write first. From the first, the second to the third, the half-life is not constant because it's not a first order reaction, it's a zero order reaction. By using our graph, we can see that the successive half-life decreases. This is for zero order reactions. For first order reaction, the successive half-life will be constant because what you get is an exponential decay kind of curve, all right? So that's the end of that 9-mark question on rate of reaction, question 7. Question 8, so another fixed assay question, but this is on relative rate of hydrolysis. So what we have is acyl chloride. Acyl chloride is RCOCl, and this is versus alkyl chlorides. Alkyl chloride is just halogenoalkane, and the next one is aryl chloride. Aryl chloride is basically halogenoarine, so it's a halogen bonded to a benzene ring, such as like this, and you have I don't know, a chlorine or bromine or whatever. Okay, and then halogenoalkane is just RCl. So in terms of these three, which one get hydrolyzed the fastest? Well, this thing is going to be hydrolyzed the fastest due to the two highly electron withdrawing groups there. Between this and benzene ring doesn't want to get hydrolyzed that much. As you know, despite the halogen being electronegative, if you look in the data booklet, the halogens are actually 246 directing. 246 directing for electrophilic substitution inside the benzene ring. That's because they actually donate the lone pair into the benzene ring despite it being electronegative. Because of the lone pair delocalization, they activate the same as the electron donating groups, meaning to say that this bond is actually much stronger than the single bond that you perceive it to be by looking at this diagram. Therefore, halogenoarine does not get hydrolyzed at all. So from the fastest to the slowest, in fact, that is the exact trend already. From the fastest to the slowest hydrolysis. Okay, so I should go a little bit, move it up there. Is that good enough? Probably not. 246 directing, probably don't want that. Electrophilic substitution mechanism. Anyway, so the slowest to hydrolyze is going to be halogenoarine, followed by halogenoalkane, followed by acyl chloride, which is very fast to be hydrolyzed. In terms of your reason, so acyl, well, first of all, halogenoarine first. As I mentioned, the lone pairs on the halogen, bonded to benzene, actually delocalizes into the benzene ring. Delocalizes into the ring. Therefore, the carbon arene, I should say the carbon bond arene with the halogen is much stronger than expected or perceived than normal carbon alkyl halogen. Okay, much more difficult to break. Okay, so alkyl halides or halogenoalkane has polar CX delta minus, delta plus. Same thing with acyl chloride. But what is different about acyl chloride is that acyl chloride also has a highly electron withdrawing carbonyl delta minus oxygen there. Acyl chloride also has highly electron withdrawing electronegative, very electronegative oxygen. Therefore, making that central carbon very delta positive, therefore susceptible. Susceptible means very prone to nucleophilic attack. Nucleophilic attack meaning like water, and therefore it is very easily hydrolyzed. Okay, so the whole idea is very easily hydrolyzed because of two highly electron withdrawing groups, this one being a more electronegative element than chlorine, therefore making this carbon very delta plus, very susceptible. Nucleophile wants to attack electron deficient, electron poor carbon, just like that. Okay, so that's it for that 3-mark essay, which you can definitely prepare for. Question 8, part B. So you have this particular drug. Ooh, okay. I'm not gonna draw the whole. Should I draw the whole thing? No, I'm not gonna draw the whole thing. Hope you can see the ester linkage. That is your ester. And then you have another ester on the far right hand side, and you have an amide. Amide is going to be this C or NH. All of these are from your O-level or IGCSE chemistry as part of polymerization. And you also learn this in AS for ester and amide in A2 for amino acids and proteins and stuff. Completely hydrolyzed under acidic conditions. So be careful, we're talking about acid hydrolysis. For ester, it's no problem, but for amide, we're going to get an amine and a carboxylic acid. The amines are basic. Which means in acidic conditions, you're going to protonate. So altogether, you get 3 products. So if I just draw out the first product, there's your OH there, and then there is your carboxylic acid there. So I'm trying to follow what I have there so that I don't have to, redraw the very, very big structure. There's your nitrogen there. That is your another ester. So this will give you carboxylic acid, and that will give you your 1 carbon alcohol again. So that is your 1 carbon alcohol there. There's your 1 carbon alcohol there. So these and these are exactly the same product. CH3OH is methanol. They say draw the structures in the boxes. They don't say skeletal, structural, or display. I can challenge you to draw display and see whether you have enough time in the exam or not, which is why you must practice skeletal. Even when you started from AS, skeletal is the way to go. Okay, if you want to excel, if you want to do well for organic chemistry. Onto the next bit, the bottom bit, I have, is that correct? No, on this nitrogen there, I still have my benzene ring. Okay, and then I have my amide there. The amide will break. What happened then is I'll get an NH like that, and then I'll get a carboxylic acid, and this is a 3-carbon carboxylic acid. 1, 2, and 3. This is from the amide. Now they get hydrolyzed. If I draw a pink boundary there. And did I say just now acid hydrolysis? You are getting an amine with a lone pair on the nitrogen. So what happened is there will be NH. Well, the nitrogen will have 1, 2, 3, and 4 because it uses the lone pair to form dative covalent bond to a H plus with no electrons. There's your AS dative covalent bond. So draw the structures for these organic compounds. I have drawn them. So there is just going to be CH3OH, and there is just going to be the propanoic acid, and I can just copy down the big organic molecule, and yeah, that's just it. Okay, so 1, 2, and 3. Do I want that? Yep, that should be all right. So just showing that that is your product 1, there's your product 2, there's your product 3. I guess what's tricky is under acidic hydrolysis, your amines will get protonated. And don't forget that this is also amine. Okay, I just want to highlight the fact that this is also amine, so this could also get protonated. I should have seen it earlier. There is a lone pair there as well, so that should get protonated as well. And when you get protonated, it's a plus. Carboxylic acid doesn't get protonated since they are acidic already, but these are amines with lone pairs on the nitrogens. They can get protonated. For that 3 marks, I don't know how much they'll penalize you if you forget that, but that is very typical in this kind of acid-base hydrolysis type of question. On to the next part. So this is question 8C. This is proton NMR. So we're looking at compound Y, C5H10O2. It can react with Na2CO3, and you get bubbles, you get effervescence, you get a gas. Anything that react with carbonate and get a gas, that gas is CO2. Therefore, Y has acidic group. Y has acidic group, something which is acidic. In fact, it has to be a carboxylic acid, because even though phenol is acidic, but then phenol cannot react with carbonate. Only carboxylic acid is acidic enough to react with carbonate. With the organic compound, and then the proton NMR in D2O. So what is shown is in D2O. So we know the OH of carboxylic acid, fast exchange. This is a concept for proton NMR, fast exchange with D2O. So you will disappears. This disappears. So essentially what is shown is 3 signal, but then you know one of the OH disappears, so you're looking for 4 signal in reality for the carboxylic acid, but don't go looking for the carboxylic acid, because what is shown is just from 0 to around give or take around 2.6 ppm. So you know the OH of carboxylic acid is much higher, which is why they say in D2O, it doesn't matter. This peak wouldn't be seen because you are in D2O. Okay, because you are in D2O, this peak wouldn't be seen at all. So out of the 3 peaks, you have 5 carbons. You have 5 carbons, and it has carboxylic acid. Looking at them, what do we see? We need to suggest a structure for it, and let's see. So if we suggest a structure for it, it's a carboxylic acid. How about if it is a straight chain? So if it is 1, 2, 3, 4, 5, so there's C5H, 3 hydrogen, 4, 5, 6, 7, 8, 9, 10, C5H10O2. You gotta think about all the possible isomers of it, but then this cannot be because it's got 1, 2, oops, sorry, I'm not looking for carbon, I'm looking for hydrogen. 1, 2, 3, and 4 different hydrogens. Why did I not count this? Because this one was already discounted from the fast exchange in D2O due to labile proton as stated in the syllabus. OH and NH is labile. Fast exchange, you don't count these because you're looking from 0 to 2.6 ppm anyway. 4 environments, you only have 3 environments, so you know you're not looking for these, so this one can't be the isomer. I can be a little bit cleverer because I see there's a doublet and a doublet. What does a doublet actually mean? A doublet means I have one neighboring protons. I have one neighboring protons. Let's see. If like that, 1, 2, 3, 4, 5, and that doesn't work, does it? So one neighboring protons, this one will see many lines. This will see one neighboring proton, so this one 4 and 5 will see a doublet. 2 will see one neighboring proton, so 2 will see a doublet. There are 4 and 5 will be the one which is just below 1 ppm because there are two environments that overlap as one. So this is the blue one, and then I can show the red one, which is 1 carbon, and I can show a black one, which is I mean hydrogen. So there is 3 hydrogen there. There is 3 hydrogen for the blue one. So for the blue one, there's 6 hydrogen altogether. And this is going to be CH3 twice CH, and you have one neighboring protons, and you have one neighboring protons means let's see, one, you are here, you have one neighboring protons, you will get a doublet. Whereas the black one is just got 2 hydrogen, and is a CH2 next to a CO2H, and when you are here you don't have any proton there, but you have 1 proton on the other side, so you also have 1 neighboring proton, and you will also be a doublet, but your intensity is lower because you only have 2 protons. So this is going to be the one which is 2.2 ppm. So that has to be the one which is 2.2 ppm. So this is 2.2 ppm. The 6 hydrogen is the one which is around 0.8 ppm. And last but not least, when you are the red color one, not the pink, the red color one, you just have 1 proton, and there has to be the multiplet, which is around 1.9 ppm. You read the middle bit, give or take. So there's your CH3 twice CH, CH2. You are what I have underlined here. You have got many neighboring protons. In fact, you have got too many to count. You got 6 and then 7 and 8. That's why you got many lines. You got many neighboring protons. You got multiplet. You got so many lines. And that's the one you saw at 1.9 ppm. So all in all, use the information to suggest a structure of Y. Y is this. Well, what I've drawn on the left, I'm just drawing a little bit neater. If you want, you can draw the structural formula. So CH3 twice, and then you have CH. There's a carbon with 4 bonds, 1, 2, 3. So there must be 1 hydrogen there. And then CH2, and then CO2H. Use that thing to work out, well, I've already worked it out, 0.8. The next one is 1.9. So what I can do is I can just move that down there. Beauty of working on the screen is I get to move things around just as easy as that. Yeah, just like that. Okay. Not very satisfied there because that line doesn't look like it is straight. Don't want to be a super perfectionist, but neither do I want to be super sloppy. That looks slightly better. Anyway, doesn't matter. So the environment of the proton is going to be this one. So this is where you are. Environment of the proton. You can obviously copy paste from the data booklet based on the description that I give you. The splitting pattern there is going to be the doublet or the multiplet or the doublet splitting pattern. Number of hydrogen atoms responsible for the peak. This is the integrated ratio, number of hydrogen atoms responsible for the peaks. So I've not done them in exact order, but I hope that makes sense in terms of what we have counted based on these particular things that we have discussed. So that's the end of these 10 mark questions. That runs up one of the most difficult concepts, which is on proton and carbon NMR. But here in this question, it's just proton NMR, part of analytical chemistry. But a lot of it just comes down to whether you can interpret and analyze all the information given. That's the end of that 10 mark question. And this is the end of this June 21 paper 4.2. So it's the A-level paper 4, pretty long by now. I better finish it as soon as I can now. Don't forget to click the button on the bottom right to subscribe to the channel, and please share the channel widely with all your friends, chat group, juniors, seniors, relative, etc. etc. You can follow me at ptet.chemistry on Facebook, Instagram, and Twitter. Send in messages, send in questions. Look forward to hearing from you, and good luck in the exams. Thank you for watching, and see you in the next tutorial video.